Okay, thanks everybody for coming. And my name is Lalith Talagala, and I work in the NIH MRI research facility. That's the facility that operates the NMRF 3T scanner. Can everybody hear me? Is that okay? Everything good? Okay. So today we'll be talking about perfusion imaging. So that means we will actually look at techniques that we can use to sensitize MR images to blood flow. And here's the outline. Today's talk, we will actually discuss two main techniques, the dynamic susceptibility contrast, that's DSC, and the arterial spin labeling technique. In both techniques, we will look at the how we acquire the signal in these methods, and also how what we have to do to quantify this signal to measure perfusion or any other parameters that we can extract. And also, I will give some examples on the way. Um, in the arterial spin labeling technique, we will briefly discuss the different labeling techniques as well. So at the end, I will actually show you some examples of doing functional imaging using perfusion rather than bold. So today's talk mainly, we will concentrate on perfusion in the brain, the cerebral blood flow, blood volume, and the mean transit time. So just to start off, so that everybody's on the same page, the perfusion by perfusion we refer to blood flow in the capillaries, and we would like to measure the amount of flow delivered to the tissue voxels. So blood flow, we will use the units of, generally the units are in milliliters per unit time per 100 grams of tissue or unit weight of tissue. And the blood volume is, of course, milliliters of blood per some amount of tissue. And the mean transit time, which is the average time that the blood takes to go through the capillary bed, is measured in seconds. Just some numbers to keep in mind here. Cerebral blood flow, milliliters per minute per 100 gram, is about anywhere from 60 to 80 in the gray matter. And the white matter is about 20 to 30. And the cerebral blood volume is about 4 to 6 milliliters per 100 gram in the gray matter, and about factor of 2 less in the white matter. And the mean transit time is around the order of 4 seconds in the gray matter, and the white matter is a little bit longer. So these numbers are actually using the current typical resolutions, about 3 millimeters. And so depending on the resolution, sometimes the values for gray matter blood flow and white matter blood flow could be different. So perfusion MRI can be performed with two very different techniques. First technique is called the dynamic susceptibility contrast, and the second technique is ASL. And so this slide shows a comparison of the two techniques. In the DSC technique, it requires injection of external contrast agent like gadolinium, and this method actually produces quite large signal changes, and therefore the acquisition time is quite fast, in the order of less than a couple of minutes. This technique is generally suitable only for a single application, because we have to inject a contrast agent, but it is widely used in a clinical setting. Arterial spin labeling, on the other hand, does not require injection of any external contrast agent. Here we use blood itself as a tracer. This method produces quite small signal changes, and therefore we have to average a little bit longer, and so the technique is slower than the DSC method, and the acquisition times are in the order of 4 to 5 minutes, depending on the resolution of the images. But because we do not require injection of external contrast agent, this method is suitable for multiple measurements, and therefore can be used in a clinical as well as research settings. This technique ASL can also be used to do functional MRI, and I will show some examples towards the end of my talk. So let's start with the dynamic susceptibility contrast technique. So in this method, what we try to do is to monitor the passage of contrast agents such as gadolinium through the tissue by some form of rapid imaging. So we here have the injection of bolus injection of contrast in the vein, and the contrast is carried by blood through into the veins into the heart and then throughout the body. So when the contrast is passing through the brain, we rapidly acquire images through the brain. Typically, this is done by using gradient echo or spin echo EPI techniques with a TR of about 1.5 to 2 seconds. So within this TR, we can actually acquire multiple slices. So and we repeat the acquisition of the same slices over and over again for about 1.5 minutes, so that we can actually capture the whole passage of contrast through the brain. In this technique, we actually use a little bit longer TE, about 30 to 50 milliseconds, depending on the field strength. That's because we would like to weight these gradient echo images for T2 star weighting, just like in bold contrast, because in order to capture the signal changes due to gadolinium traversing the blood, traversing the brain. Okay, so let's see how the dynamic susceptibility contrast works in practice. Here's my cartoon of a tissue voxel without gadolinium. And then we have the other situation when the gadolinium is within the blood has filled the tissue voxel. So gadolinium is paramagnetic, and also it stays in the stays intravascular unless the blood-brain barrier is broken. It stays in blood. And so when gadolinium arrives at the tissue, we would have a different magnetic susceptibility between the blood vessels and the tissue, and therefore we will have a increase in the magnetic susceptibility difference. That leads to an increase in field inhomogeneity within the tissue voxel, which leads to increase in the R2 star relaxation rate or shorter T2 star. And under these conditions, if you use a gradient echo and spin echo MRI, you will see a signal loss. So when the gadolinium is passing through the brain, we expect a decrease in the MR signal with gradient echo EPI. So here's an example of series of images acquired while the gadolinium is passing through the brain. These images were acquired with echoplanar imaging, gradient echoplanar imaging at 50 milliseconds. This is a 1.5T images. So you can see at the top row, this is the baseline condition. We have high signal throughout this slice. This series of images represent the same slice acquired over and over again with a TR of about 2 seconds. So we have high signal intensity as a baseline, and as the gadolinium arrives, we see the signal starts to decrease, and we have a maximum signal loss. And then as the gadolinium washes out, we will see the intensity returning back to the baseline condition. So you could actually see what happens in this case better if you extract a time course from a single pixel throughout the whole image series. Here I have done that for 2 pixels. One is a gray matter pixel and another pixel which is mostly blood. You could see the baseline signal is high while the in both cases, while the gadolinium is washing in to the tissue, we see a signal drop, and signal drop becomes maximum at the highest concentration of gadolinium, and as it washes out, the signal returns back to normal. And you could see that the signal loss in the blood pixel is much higher than the signal loss in the gray matter pixel. And this is because the concentration of gadolinium in blood is much higher than in gray matter. And this first signal loss is called the first pass because that is the first passage of gadolinium through the tissue. And after the first pass, sometimes you see the gadolinium coming back for the second time around, and that phase is called recirculation. So we can see here now this signal loss is depends on the constant amount of gadolinium present in the voxel. So therefore, there is some, we can actually get some information about the concentration of gadolinium at different points in time. Okay, so so as I said, the signal intensity when the gadolinium is passing through the brain depends on the amount of gadolinium present in the voxel, and therefore we should be able to get some information about the concentration of gadolinium at different points in time. And early work in this field has demonstrated that the change in relaxation rate due to the presence of gadolinium is roughly linear with concentration. And also we could actually write the signal intensity in the presence of the contrast agent, gadolinium, how it relates to the baseline signal with this equation. And combining these equations, we could actually calculate the concentration of gadolinium using the ratio of the signal intensity in the presence of contrast to the baseline signal intensity and the logarithm of that ratio. And these are, the K is a proportionality constant, and it has to be scaled by TE. So we can use this equation to convert the signal time courses that we saw earlier to concentration time courses by pixel by pixel. So here we could see that the concentration of the gadolinium is much higher than the concentration of gadolinium in gray matter. So at this point, what we have is two pieces of information. So with this information, we would like to find out how we can actually measure the cerebral blood volume, blood flow, and the mean transit time. Here's my cartoon of the tissue with the inflow, with the flow milliliters per gram. And what we have is a concentration time curve in an artery that's supplying the tissue, and also the concentration time course in the tissue. So concentration time course in the artery is called the arterial input function. This is like what we measured in the artery. And the concentration time course in the tissue is called the tissue response. So we could combine this information using tracer kinetic theory. We can actually determine the CBV and the CBF. So the results of that, by applying the tracer kinetic theory, it turns out the cerebral blood volume can be measured by taking the integral of the tissue concentration curve divided by the integral of the arterial concentration curve, which represents the ratio of the areas under these concentration time curves. And KH and rho are constants that takes into account the differences in the hematocrit in the large and smaller vessels, and rho is the density of the tissue, just to make sure we get the units correct for CBV. So measurement of CBV is fairly straightforward, but the calculation of blood flow and mean transit time is a little bit more involved than that. It turns out, according to the tracer kinetic theory, we could write the tissue concentration, that's tissue concentration over here, as a convolution between the arterial input function and also another function called, which is a residue function. So this residue function is a characteristic of the tissue that you are observing, and this equation is scaled by the cerebral blood flow, the amount of blood being delivered to the tissue. So in this equation, we have two unknowns, that's the scaling factor as well as this residue function. And therefore, in order to find the scaling factor, we have to deconvolve this equation. And the result of that is a scaled version of the residue function. So because the scaling factor is dependent, is equal to the cerebral blood flow, we could measure the cerebral blood flow as the initial amplitude of this scaled residue function. So, and when you calculate the CBF, and then we have previously calculated the CBV, so we can calculate the mean transit time as the ratio of the CBV and CBF. So now we have a framework to calculate this CBV, CBF, and mean transit time, and we could apply these calculations on a pixel by pixel basis. And here's an example of CBV maps, CBF, and mean transit time maps. They're calculated from the data that I showed you a few slides earlier. And here you could see that in this particular case, the right hemisphere, we have increase in cerebral blood volume compared to the left hemisphere. And also the cerebral blood flow is increased in the right hemisphere compared to the left hemisphere. And the mean transit time is actually decreased in the right hemisphere compared to the left hemisphere. So as I mentioned, this technique within the repetition time of TR, we can get multiple slices. Therefore, we could actually get these maps across multiple slices. Here are the multiple slices from the same data set. We can see this patient had a tumor in the left hemisphere. That's why we have the elevated CBV and CBF and the mean transit time. And by acquiring these images, we can get characterize the different pathologies in using this technique, and therefore this method is widely used in a clinical setting. And here's an example of a subject without any pathologies. And here you could see the gray matter perfusion as higher than the white matter perfusion. And we could see the perfusion across multiple slices is quite homogeneous in gray matter and white matter. And something that to note in these type of images is that very high signal intensity in the blood vessels. Here is the middle cerebral artery. So this high signal intensity in the blood vessels can sometimes mask the small pathologies near those blood vessels. So therefore, that's something we need to watch out for when you look at these images. So during DSC quantitation, the errors can occur for a variety of reasons. If you remember, we assumed a linear relationship between the change in the relaxation rate and the contrast agent concentration. Recently, there have been several reports that describe that this assumption is not true, and therefore, if you don't take into account the true relationship, we would have errors in our computation. And also, the arterial input function determination can be quite problematic because of partial volume in the different orientation of vessels, and sometimes the arterioles, the signal loss in the arteries are so great so that the peak, it's hard to determine the peak signal loss. And also there is dispersion of the arterial input function from the point you measure and to the location of the tissue. So therefore, if the arterial input function is not quite correct, so therefore the deconvolution is not going to give you the right residue function, and that means the scaling factor that we will determine as the cerebral blood flow would be not correct. And and also the deconvolution process it can be problematic because it's quite sensitive to noise. Unless you use a proper technique, this could be introduce errors as well. So therefore, this technique is good for measuring relative blood flow and blood volume maps. And if you want the absolute blood flow and blood volume measurements, then you have to acquire calibration data and use the scaling factors to rescale the relative images to get absolute values. Okay, at this point, let's look at the arterial spin labeling technique. So in this technique, we do not use a external contrast agent. We try to use blood itself as a tracer by magnetically labeling or tagging the blood before it reaches the brain. By tagging or labeling, I mean that we actually invert the longitudinal magnetization of the blood in the neck region so that the inverted blood would flow into the brain, and then we can image the brain when the brain is brain tissue is filled with inverted blood. So what we would like to do is to measure the signal change due to the inflow of the inverted blood. So in this case, we have to have a control condition where the proximal blood is not inverted. So we have two sets of images. One is the control image where there is no inversion of incoming blood, and then what is called a label image where we had inverted the longitudinal magnetization of blood that flows into the brain. The difference in these images, the signal change in these images, is related to the amount of blood flow that arrived at the tissue, and therefore we should be able to calculate the perfusion using the change in signal. So in this experiment, there are different phases. There is what is called a labeling phase, where during this period we tag or invert the incoming blood, and then we wait for a certain amount of time, about 1 to 2 seconds, for that inverted blood to flow into the brain tissue, and then we image. So imaging can be done with any imaging technique that you have available. It could be 2D, 3D, or EPI, or these days people are actually using even spiral images. And in this case, we use the minimum possible TE because we want to get the best possible signal-to-noise ratio. And also, it is not necessary to weight these images in a particular fashion, because what we are interested in measuring is the change in longitudinal magnetization. So therefore, like shortest TE possible is the one that is advantageous. And these experiments generally take about 4 to 5 minutes. So here's an example of the type of images that we acquire in arterial spin labeling. On the top left, you could see a control image. These are echoplanar images. So this is control image. I have not inverted or tagged the incoming blood. So therefore, the pixel intensity in this control image represents the signal from the static tissue, as well as the signal from the blood that is in that tissue voxel. So it's the sum of these signals is represented in the control image. So whereas in the label image, where I have tagged or inverted the blood, incoming blood, so therefore this signal intensity in this image represents the static tissue minus the blood signal that is contained in that voxel. So by subtracting these two images, we can isolate the signal due to the blood within each voxel. So here's an example by subtracting one pair of control and label images. You could see that the signal-to-noise ratio is quite low because the blood volume within the voxel is quite low. But so if you do this experiment multiple times, and here's an example where I have averaged it 24 times over 4 minutes, you can improve the signal-to-noise ratio. So these images are called perfusion, qualitative perfusion images or difference images. And typically what we are looking at is in gray matter, we have about a 1% signal change due to blood tagging. And in white matter, we should get about 2% signal change. Yeah, it goes as control label, just keep going, yeah. Yeah. We don't have to wait for a full recovery of 5T1s, but you will be using a TR about 3 to 4 seconds or so, generally. Okay, so let's look at the different strategies for labeling. Depending on the strategy that you employ to label the incoming blood, these experiments are called either pulsed ASL or continuous ASL. So in the pulsed ASL technique, what we do is to label or invert invert the magnetization from a large slab below the brain. So all the blood within that slab would then be inverted, and then that inverted blood would flow in to the brain when we image. So in this case, we have a wide labeling slab, which is created by a typical 180-degree pulse, which takes a few milliseconds. Now, in the continuous ASL case, what we do is we apply a radio frequency pulse and a gradient to define what is called define a narrow labeling plane. So all the blood passing through that labeling plane gets inverted by a process called adiabatic fast passage. So in this case, because this is a narrow labeling plane, we have to keep that labeling on for a longer duration so that we have enough blood passing through that plane, and we would then be able to capture the signal change, a significant signal change. So in pulse ASL, the approach is to quickly invert a large slab, whereas the continuous ASL, the approach is to define a narrow labeling plane and keep it on for a longer duration. So how do we quantify the signal change to get CBF? So as I mentioned, now what we have is a change in the signal that we have determined between the controlled images and the labeled images. We have to normalize that from the equilibrium signal, and that is a qualitative perfusion map. And this is a scaling factors that you need to apply to convert this qualitative perfusion value to blood flow. So these scaling factors depend on the relaxation rate of blood and the labeling efficiency, as well as the pulse sequence parameters that we call as labeling time, the post-labeling delay, and the partition coefficient of order. So in these scaling factors, what we have to look at is that which one of these parameters are likely to change from patient to patient, because in general, or subject to subject, in general, we do not measure these parameters from subject to subject. The parameter that is most likely to change is this labeling efficiency, which tells you how well we invert the incoming blood. When the incoming blood is inverted perfectly, the alpha is 1. When the incoming blood, and it is less than 1 if it is not perfect. So in the pulsed ASL scheme, the alpha is taken as 1, whereas the continuous ASL alpha is quite high, around 0.8 to 0.9. So this labeling efficiency can change a little bit from subject to subject. So since we don't actually measure this in every study, so therefore a little bit of, we will have a small variation of cerebral blood flow due to the error in the labeling efficiency. So the measurement of CBF using ASL is quite straightforward because it requires applying a scaling factor to the fractional signal change that we measured. So if you look at, let's look at the pulse labeling scheme a little bit more closely and how it works. So as I mentioned, in pulse labeling, the idea is to actually invert a large slab, a tissue within a large slab below the neck, and here the white arrows represents the status of the longitudinal magnetization of blood within the tagged region. So after inversion with an RF pulse and a gradient, we have the magnetization of the blood inverted. And in the subsequent period, you will see that these white arrows will move to the right towards the brain. And here's an example of just before the next RF pulse, it would have traveled further down towards the brain. And at this point, in this technique, we applied a saturation pulse to the same slab that we applied the inversion pulse to. Here's like shown as the gray area in this slide. And the idea, idea here is to actually define a region of blood that is um, um, truly inverted and make a well-defined region. So in this case, we have the blood within this slab that has moved forward compared to the previous location, has been inverted, and everything below that has been saturated. So in the next time period, we will have this blood that has been inverted, arrives at the tissue voxel and will actually exchange with tissue or will be present in the tissue. So if you, it is instructive to see what the status of the blood during this pulse sequence at the voxel level. So if you think of a particular voxel in the brain and see what type of blood is coming into the voxel during this pulse sequence, you will see initially the blood that is arriving at the voxel has the longitudinal magnetization in the plus z-axis or unaffected, and after a while, from this point on, you will see that the blood that arrives in the voxel, the magnetization has been inverted. And by the time you image, it is possible some saturated magnetization arrives in the voxel as well. So this is the labeled condition. And so what we then need also the controlled image condition. In this case, we turn off the gradient during the initial 180 RF pulse, 180 degree RF pulse. So therefore, in this time period, we don't have any inversion of the blood within the slab. And so therefore, these white arrows are all pointing up, whereas in the label case, the white arrows were pointing down. So now the blood that has not been inverted flows into the tissue, and they will remain along the z-axis and unaffected while they arrive in the tissue voxel. So in this case, voxel view would show that all the blood arriving in the control condition, all the blood arriving at the tissue would be unaffected, and their magnetization would be along the z-axis, and similarly to the label condition, depending on when the images are acquired, some saturated blood will be arriving at the tissue. So the image that you acquire is actually the net result of all the blood that has arrived at the voxel. Signal intensity of the image you acquire depends on the net result of all the blood that have arrived at the voxel during this pulse sequence. So you could see that the difference in signal that we get from the label and the control images is due to the change in magnetization during this period. During the labeling, it's inverted. During the control period, it's not inverted.
So one question here, you said you just switch on the gradients as compared to labeling versus control.
Yeah. In this case, what we do is we apply a 180-degree inversion pulse to this area, right? So, and that requires a RF pulse as well as a gradient. By turning the gradient off, so there is no definition of, there is no slice selection. So therefore there is no inversion in that region.
So it would be inversion of the entire brain, right?
No, but this pulse is off resonance, right? Mm-hmm. So it is not going to affect the rest of the brain. Okay, so here's an example of data acquired with the pulse labeling scheme. Here's some control images, and in the bottom row, you see the difference images. These are images that have been control minus labeled images that have been averaged for several minutes, and you could see that's a very good differentiation between gray and white matter contrast. Advantages of this sequence is that it has a high tagging efficiency and low radio frequency power deposition, and also it's very easy to implement because it's a simple pulse sequence that you can program on the scanner and run. But the disadvantage here is it's difficult to actually get whole brain coverage without sacrificing a lot of sensitivity. Okay, so at this point, let's look at continuous labeling. So if you remember the continuous labeling, we define a narrow, very narrow labeling plane, and this is done by applying a radio frequency pulse in the presence of a gradient. The frequency and the gradient strength that we apply defines the location of the labeling plane that I show here in orange. Now, in this case, what happens is when the blood crosses this labeling plane, it gets inverted in the process in the process called adiabatic fast passage. So at the beginning of the pulse sequence, we see that on either side of this labeling plane, the magnetization of blood has not been affected at all because we just started the experiment. And after a certain time, you will see some of the blood has crossed over to the other side, and whatever the blood that has crossed over to the other side would be inverted, while the blood that has not crossed over will still be unaffected. And this blood over here, the magnetization pointing outwards, was never crossed the labeling plane at all. So as time goes on, we will have more and more blood crossing over the labeling plane, and at some point we would have all the blood to the right of this labeling plane would be inverted, whereas everything to the left of this labeling plane would be unaffected. So then we will actually wait for a little while for all the blood to arrive at the tissue voxel, and here's a situation where you have now all the inverted blood has arrived at the tissue voxel, and the rest of the blood vessels are now filled with the blood that has not been inverted, because during this time we have turned off the labeling, and so this labeling plane is not active during this what is called the post-labeling delay. So by doing that, we would be acquiring the labeled images, and the control condition is where we actually turn off this RF pulse. When the RF pulse is not present, there is no labeling within that plane, so all the blood passing through that plane is will not be affected at all, and therefore the image that we acquire represents a control image. So here again, our view from the voxel, we see for the labeled images, we have the blood arriving in the voxel unaffected for a certain amount of time. Then we have labeled blood arriving at the voxel. And then at the end, we might have again some blood that is unaffected arriving at the voxel. Whereas in the control condition, all the blood that arrives in the voxel has not been affected at all. So therefore, the difference between these two conditions represents the change in, represents the inverted blood that arrived at the voxel during this pulse sequence. So this method is most easily implemented by using a coil that is dedicated for labeling. In this case, we call this a neck labeling coil. So here you see a subject with a neck labeling coil placed on her neck. So this neck labeling coil is constructed as two rectangular loops, so that when you place on the neck, you could see that the radio frequency penetrates into the neck, so that all the blood vessels in the neck will be exposed to the radio frequency field. So when you apply this radio frequency field in the presence of a gradient, it defines the labeling plane that we want. So all the blood passing through that labeling plane would would be inverted as long as the radio frequency pulse power is applied through this coil. So the advantages of this technique that it can provide whole brain coverage, because when we have a local coil like this, the radio frequency field is concentrated near this local coil and it does not affect the brain signal, and therefore we can actually image the whole brain without any without it being disturbed by the labeling RF. And this technique can give you high labeling efficiency. And the big disadvantage of this technique is that it requires special hardware. So because these labeling coils, this type of neck labeling coils are not provided by the manufacturer. However, this technique can give good results. Here's some example of data that we collected quite a long time ago. On the left, we see the difference images, difference control minus label images, qualitative perfusion images. And these days we used to actually use a slightly different model which required us to measure the T1 maps corresponding to these sizes in order to convert these signal changes to cerebral blood flow maps. So here are the relaxation rate maps that has been used to convert these signal changes to the CBF maps. Here we can see the blood flow in the gray matter throughout the brain, whole brain, quite nicely. And these images were acquired at quite low resolution at 3T with a head coil. This is before we had access to multi-channel receiver coils. And here's an example of the continuous ASL experiment with a neck labeling coil performed with an array coil. Here again, this data was acquired a few years ago in the 8-channel array. We could see the good signal in the gray matter and very good contrast between the gray and white as well. These are quantitative CBF maps, and these images can be acquired in any orientation. On the left is the axial and the right is a coronal. These were acquired in about 5 minutes at a resolution of 3 by 3 by 3. Here's another example of continuous ASL performed on a patient with hemangioblastoma. You could see the tumor, very high blood flow in the tumor and no blood flow in the central part of the tumor. And you could see the tumor, the blood flow is much higher than the background gray matter blood flow. And the same tumor is in the axial plane, is shown in the middle over here. And the corresponding, the image on the right, lower image is actually the corresponding, the post-contrast image, where you inject the contrast and look and image after the contrast has had time to get into the tissue. And in this case, you could see that the contrast has leaked into the center of the tumor, and therefore you cannot really see where the high flow area of the tumor compared to the central region. And this patient also had some tumors slightly below the cerebellum, and we were able to detect that as well, because the labeling in this case was performed down below in the neck region, so all the blood vessels supplying these tumors below the brain were also labeled, and also we were able to detect the signal from that. So other techniques we may not have been able to see that, because the other techniques would require labeling inversion pulses applied in this region, so that that region will not be seen as in the perfusion images. We have also extended this technique, continuous ASL technique, to 7T. And at 7T, we actually made a neck labeling coil similar to the 3T case. And these experiments were done using an 8-channel array. And here are some example images. Here, the top row are the perfusion difference images, again showing good signal from the gray matter and good contrast between the gray and white matter. And these images were acquired with the frequency of the RF pulse during the labeling condition applied with the proper frequency. And the bottom row of the images, we have purposely actually made the frequency negative to make sure that we do not see any residual signal. So this set of images confirms that the images that we see on the top row actually signal is coming from due to blood flow and not due to some artifact. So in this case at 7T, we were able to, these images were acquired at 2 by 2 by 3, a little bit higher resolution than we were able to do at 3 Tesla, and these images took about 8 minutes. Here are some quantitative CBF using continuous ASL. So here what I would like to point out is now we were able to quantify the signal changes, the perfusion signal changes that we acquired using the scaling factors that I showed you earlier. And in this case, the signal changes in gray matter was measured to about 1.5%, and the white matter is quite low. And the CBF was quantified to be around 70 in gray matter and around 25 in the white matter. The resolution again here is at about 2 millimeters by 3 and acquisition time of 9 minutes. So as I said, the continuous ASL works well, but it requires special hardware. So that's it. So it wasn't. So it's difficult to implement. And last few years, we saw the development of the technique called pseudo-continuous ASL, which does not require special hardware. And in this technique, what we try to do is to mimic the continuous ASL technique, but instead of actually having the radio frequency pulse continuously on throughout the labeling period, in the pseudo-continuous technique, we apply a train of RF pulses, short RF pulses, in such a way it actually accomplishes the same, it has the same effect as the RF is applied continuously. And in this case, because we are applying a train of RF pulses, the gradient is also modulated to match the RF pulses. And so in this case, we have a labeling, we define a labeling plane, again, below the neck. This labeling plane is a little bit wider than in the continuous ASL case, but in this case, also the blood that crosses this plane gets inverted through similar, in a process similar to a diabatic fast passage. So advantage of the technique, again, it can provide you with the whole brain coverage with high labeling efficiency, and most of all, it uses standard hardware. So therefore, this is implemented as a simple pulse sequence that you can run on the scanner without too much difficulty. So disadvantage is that it has a little bit higher RF power deposition, and also it is sensitive to off resonance effects that might be problematic at higher field strength. So here's an example of pseudo-continuous ASL at 3 Tesla. We see good gray matter signal at resolutions around 3.5 millimeters in a scan time of 5 minutes. We have also extended this technique to 7T, but the 7T was a little bit problematic because of the off-resonance effects. We had to acquire additional calibration data to correct for off-resonance effects. But once you do all the corrections, you could see that you can get good images at 7T. These were again resolutions of 2.5 to 3 millimeters in about 4 minutes. So I mentioned before that the ASL can be used to do functional MRI in addition to measuring steady state perfusion. You can also be used to as a way of performing functional imaging. And here's an example of a finger movement task done using the continuous ASL technique. We see the activation due to finger movement throughout the motor area, as well as the subcortical region and the cerebellum. And in this case, we were able to um, detect changes in blood flow in the contralateral hemisphere, that is actually reductions in blood flow rather than increases in blood flow. So these functional images represents sensitive to changes in blood flow rather than bold. And one of the advantages here is that if you do functional MRI with based on perfusion or using ASL, you can quantify the change in blood flow due to a task. So here's an example of the motor activation performed using continuous ASL. And here we've quantified the change in blood flow during the motor task. And in this case, these are about 3.5 millimeter resolution images. We were able to measure blood flow changes up to 70% due to the motor task. At higher resolution, the blood flow can be measured almost 100% changes in blood flow in the motor areas. So the feature that is important here is that with ASL you could have a quantitative measure of blood flow due to the task, which is physiologically meaningful as opposed to in bold, but we can only tell what the signal change is. So ASL can also be used to perform functional connectivity studies. The top row is a set of perfusion images with overlay of the correlation coefficient maps. And here what we have done is a perfusion time series has been correlated with a seed-based time series from a seed ROI, and you could detect the correlations across the different hemispheres as across the multiple slices. And here's the bold data corresponding to the same slices. So in the ASL time series, we have made sure that there is no bold contamination by making sure that the ASL signal was filtered properly using a high-pass filter. So again, here in the functional resting state functional connectivity with ASL, if you use ASL for resting state functional connectivity studies, you can quantify the fluctuations in blood flow during resting state. In this case, we were able to quantify these fluctuations, about 30% changes in fluctuations in blood flow from the resting state condition. And the corresponding bold data showed about 0.3% change in the signal. This data required quite a long acquisitions, about 10 minutes, and pretty low resolution, about 3.75. So there are several groups have been working on this technique using ASL for resting state fMRI, and one group has taken this technique and expanded further, and there they have actually used the bold resting state maps and the perfusion resting state maps, and they combine them to measure the fluctuations in CMRO2. So I think that's a nice advancement of the technique. So in summary, we have looked at the dynamic susceptibility contrast technique. It requires contrast administration, and acquisition is quite fast, and can provide whole brain coverage perfusion maps. but the absolute quantitation is somewhat difficult, but not impossible with calibration data. Then we have the ASL technique where no contrast is required. The acquisition time is around 5 minutes and can provide whole brain data. Absolute quantitation is possible, and we have robust sequences in all the scanners, and this can be used in clinical and research work. Thank you.